Hello. The countdown thing just did something really weird, and I think I've started, so yes, let's get on with it. Hi, welcome to the last talk of the conference, Futurology for Dummies. Have you had a good 3 days here at NDC, or 5 days if you did workshops? Until now, yes, well done. I've had a great time. I had this talk prepared like a whole week ago, and so I've actually got to go to see some talks. I just went to see Kendall Miller talking about CPUs and how they work, and it's interesting stuff. So the reason for this talk is that this year is the anniversary of me getting my first job in programming. 1989, I left school at 16 and managed to land a job, almost an apprenticeship, with a local software company who taught me to code. And so I've seen everything that's happened over the last 30 years, and if you'd asked me 30 years ago to predict where we'd be now, I would have got it hopelessly wrong. So I thought, who better then to predict where we're going to be in 30 years from now? Me, yes. So that's what we're going to do. So let's just take a quick look back at 1989, my first job. I turned up. What did we have to work with? Well, this was the first server I ever worked on. This was a Tandon 286. It had 2 megabytes of RAM, 150 megabytes of spinning hard disk, and we had 8 programmers working on it at the same time. And it was not a fast machine. It ran on an Intel 802086 processor, and this was very, very early stuff. So the specs of this processor, it ran at 8 megahertz. So your processor now probably runs somewhere between 4.5 gigahertz. So it's like 500,000 times faster than that. It was just one core, none of this multi-core stuff. It had 134,000 transistors on it. Each of those transistors was 1.5 micrometers across. It was a 16-bit processor. It could address up to 16 megabytes of RAM, if you could afford 16 megabytes of RAM, because that was expensive. It would do 1.6 million instructions per second, integer operations per second, and flops weren't a thing. You could actually get a coprocessor, the 8287, which was a floating point coprocessor, which would do like a couple of 100,000 floating point operations per second. This was what a 2 megabyte chunk of memory looked like back in those days, and it had 30 pins, 8-bit data width, so you get 8 bits at a time off it. And this was what the 150 megabyte hard disk looked like. This is a 5.25 inch full height SCSI hard disk. This cost about £2,000 for 150 megabytes. And to give you an idea, because you can't really tell from the slide, of how big this thing was, that obviously is a Matchbox toy bus, and if you think of it as a Matchbox toy bus, that's probably about right, actually. And so there were 8 of us working on this 286, and we couldn't all just huddle around the keyboard like in the sketch. So we had a dumb terminal. This was a Wyse 50, and this was a black and white. It wasn't black and white, because actually black and white was really expensive, so it was either green and black or orange and black, depending on which model you got. Orange was nicer to sit and stare at all day. It was 80 by 24 characters. It didn't really do graphics. It used the ANSI character set to draw boxes using the curses library, yay. And it actually worked by pretending to be a teletype back in those days. So it said, I'm a printer connected to the network, send me print codes. And that was how that used to work. What an actual printer looked like in those days was this. This is, I think it's an Epson LX20, it's whatever this is. It's a dot matrix printer. And this was what we used to use to print out our code if we wanted to be able to see more than 24 lines of it at a time. And did anyone, if you don't remember dot matrix printers, if you're like young, and you've never experienced one of these, this is what it used to sound like. That brings back memories, doesn't it? Oh, yes. So we did actually have laptops in those days. A lot of people think laptops were more recently invented. This was a laptop back in 1989. This was a compact portable SLT286. This had a monochrome, tiny little low-resolution screen. It had 640K of RAM, and it weighed 6.4 kilos. So it was quite heavy, and it cost about £6,000. So we've come quite a long way since 1989 in the last 30 years. These days, in 2019, the state of the art in CPUs in 2019, it's not even an Intel CPU. The state of the art at the moment is the Apple A12X. That's the processor that's in the iPhone XS and XS Max. This thing runs at 2.5 gigahertz. It's got 8 cores. It's got 10 billion transistors in it. And most of those are actually in not the CPU cores, they're in things like the neural processing unit for doing much more complicated stuff. It's a 7 nanometer process now, so they're much smaller. It's 64-bit, it can address, well, I don't know what it can address. It can probably address like millions of gigabytes of RAM. The phone that it comes in has up to 6 gigabytes of RAM. It doesn't really worry about what MIPS it can do anymore. It can do 5 teraflops, 5 trillion floating point operations every second. And it's not that long ago that to get something that could do trillions of floating point operations per second, you were talking supercomputers in big air-conditioned rooms built by Cray or NVIDIA or whatever, and now we've got that on a chip. So, you know, there's the comparison between those two processors. The thing from 1.5 micrometers to 7 nanometers, it's hard to really visualize what that means. So I've made a visual aid. If this on the left is a 1989 transistor on a 286 chip, then this is how much smaller the chip is today. Yeah. It is actually still there. It's just, where are we? It's just about there. It's a pixel. It stayed, I managed to get it to stay to 1 pixel, but that is the effective difference. And this has happened, this is in accordance with Moore's law, which says the number of transistors in a dense integrated circuit doubles about every 2 years. And actually, after Gordon Moore coined that law, Intel revised it to every 18 months in line with what they were actually achieving. And so we've got billions of transistors on a chip that's smaller and faster and cooler in temperature and in just wow. And you know, that's the progress we've made there. On the storage side of things, that 150 megabyte disk that you would have to lift with 2 hands, those things were heavy. Now, Samsung have just demonstrated a 4 terabyte micro SD card. And so if you actually put that 4 terabyte micro SD card next to that disk, it would look roughly like this. That's about the size comparison there. And the state of the art in laptops, if you said to me, Mark, that talk was so good, I want to buy you any laptop you want. No? Okay. This is the laptop I would ask you for. This is the current top-of-the-range Lenovo ThinkPad Extreme. It's got a 6-core i9 CPU and a 4K touchscreen and 64 gigs of RAM and multiple solid-state disks, and it costs less than half what that compact used to cost. So things have got smaller, they've got faster, they've got better. We're just generally having a really good time. And that is without even talking about the things that just didn't exist at all in 1989 when I got my first job in computing. Now, the first one, this still kind of throws me, because I think, has that not been there all my life? The internet. Okay, the internet existed, DARPANET and ARPANET, and all the computers connected to each other, but the World Wide Web didn't exist in 1989. Tim Berners-Lee did not invent that until '93. And so I spent the first 4 years of my career where if I wanted to know how something worked or how to do something, or more likely, how to exit VI, I would have to go and I would get a ring binder which had all the loose leaf documentation, of which about a third of the pages said this page intentionally left blank, and a third more of the pages were blank, but not intentionally. But yeah, we just didn't have the internet. It wasn't a thing. We certainly didn't have Wi-Fi or mobile networks. I think we had car phones, like rich people had car phones, and the massive Motorola bricks with like a briefcase attached, because batteries were still quite big things in those days. But no, there was no networking, there was no Wi-Fi, there was no omnipresent data. There was no cloud, obviously. If you wanted hardware to run your software on, you had to buy that hardware and get it delivered to your office and set it up. And we definitely didn't have mobile devices. We didn't have phones in our pockets, we didn't have iPads, we didn't have tablets, we didn't have any of that sort of stuff. The first one of those that popped up really was the Apple Message Pad, the Apple Newton technology, which came along in 1993. Did anyone ever use one of these? Yeah. Were they shit? Yes. That thing was enormous. That thing weighed over a pound. It was 640 grams. So this was not light. I've got laptops now that weigh less than this thing did. Now, the equivalent of that is the Apple iPhone XS, which has got just so much more memory. The Newton had a 2-color screen. This thing's got all the colors. And that's 25 years from one of those things to the next. So we are making a lot of progress in technology, and it's kind of accelerating. Let's look at what some of that progress is. It's getting faster, so chips are getting faster, computers are getting faster, data transmission is getting faster, all that stuff's getting faster. It's definitely getting smaller. We're now building things that are so tiny that you actually can't see it without a microscope or something. It's getting lighter, so we can carry stuff around. I've got a computer on my wrist right now that is probably many thousands of times faster than that Tandon 286 was, and runs for 2 days on a charge. It's getting preciser, so we're getting better at creating precision hardware and so forth. It's getting powerfuler, because I had to start making up words to go into this list, and it's getting connecteder, because if you're going to make up words, then why not just go for it? So, my new hobby is to take what I've learned from those 30 years and try to apply it so I can extrapolate from where we are now over the next 30 years, look at the technology that we've got at the moment, and go, right, what's that going to look like in 10 years, 20 years, 30 years' time? So that's what I'm going to try and do. So if we extend Moore's law out to 2049, then we can expect that a single processor is going to have 328 trillion transistors on it. I'm going to be bold here and go, no, it won't. Moore's law, it's done. If you were in Kendall's talk on CPUs, transistors aren't going to get that much smaller, because we are actually hitting up against the fact that that's an atom now, and you can't make things smaller than an atom, except maybe by going to a smaller atom. And there's only so much compute you can do with a hydrogen atom. And you can't make the CPU bigger to fit more transistors on it because of the speed of light. Everything on that core has to be able to stay in the same state, and so it can only be up to a certain size, otherwise it can't operate as a single cohesive unit. But there are lots of possibilities for where processors are going to go. So right now, we've got ARM CPUs are now being built on a 7-nanometer process. Intel, you may have noticed, have been struggling to hit their 10-nanometer target, and they might be even jumping it and just going straight to 7. But with just silicon on chips, that's kind of, we're not going to get much smaller than that. So now they're looking at using alloys like silicon germanium and using germanium arsenide to alloy with the silicon so that they can create smaller transistors. But even that's going to take you down to maybe 4 nanometers, and then we've hit the effective limit of what we can do with silicon. There's a lot of research going on at the moment into graphene and carbon nanotubes, because apparently there is nothing that carbon nanotubes can't do. My new business plan is I'm going to invent a toothpaste with carbon nanotubes in it, and I'm going to charge 25 quid a tube for it. And people will go, why is this good? And I'll say, carbon nanotubes, and they'll go, yes, we understand. But they are trying to make graphene chips and processors and everything, and that will take us a little bit further, because that is getting to the point where you treat each individual carbon atom as a transistor or as a component in the processor. We also have photonic processors, light. People are building processors using photons as the unit of information and bouncing those things around the place. There's a lot of research going on into organic processor design, because the best computer that we know of is inside our heads. And even the brains of something like a pigeon is much more powerful than the Apple A12X. And those are being underused, really, pigeon brains. We could probably harvest pigeons and use them to do something more interesting, I think. And then, of course, there's quantum processors. And we're at the very early stage of quantum computing, and it makes no sense. I was trying to learn about it and understand it so I could talk about it, and I've come to the conclusion that if it makes no sense, that's how you know it's quantum. So a 64-bit register in a regular CPU can hold a number from long dot min value down up to long dot max value, which is quite a big number, okay? We had to switch to 64-bit numbers for storing the number of milliseconds since the 1st of January 1970, because otherwise dates would have stopped working a few years ago. In a 64-bit quantum computer, each register can hold 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,616 different values at the same time. If somebody actually manages to build a 64-qubit quantum computer, it will be able to crack a 1024-bit RSA private key in less than a millisecond. And it actually, make that 2040, make that 4,000, just name a bitness. It will just do it. You just go, what are the factors of that? And it'll go, they're these. And so it's going to break cryptography, but then we're going to use these quantum things to do new cryptography with 18 quintillion bit private keys, and everything will just keep going. At the moment, quantum computing is quite complicated. The best way to do it involves using Bose-Einstein condensate. Bose-Einstein condensate is a state of matter that only exists at 0.1 Kelvin, or minus 273.7 degrees Celsius. I'm not translating that into Fahrenheit, Americans. Just do it yourselves. But, 30 years ago, the 286, and now we've got what we've got now. So in 30 years' time, it's entirely possible that I'll have a quantum computer on my robot wrist that I've had my arm replaced with. So, trends we are seeing at the moment, things that have just kind of started, just kicked off. I did a bit of research for this. As I was making the next slide, I connected to my router. I've got a Netgear Orbi router, and I said, give me a list of all the things that are currently connected to the Wi-Fi in my house. 8 computers, desktops and laptops, 8 phones and tablets, 2 Xboxes, 1 PlayStation, 2 Nintendo Switches, the TV in the living room, 3 Sky Q boxes, 2 Fire TVs, my wristwatch, my wife's wristwatch, 6 Amazon Echo devices, Alexa or whatever you want to call her, 3 Kindles, quite a lot of the light bulbs, the doorbell, the washing machine. When the washing's finished in my house, the washing machine sends a message out over the Samsung SmartThings hub, and I get a little pop-up on the TV that goes, the washing's finished. There's a printer, there's a camera, and you know, that was just, I ran out of space on the slide. Out of all those things that are connected to the Wi-Fi, these are not really what you would think of as a computer. So the 8 computers and the Xboxes and the PlayStation, those have all got Intel processors in them. Everything else has got an ARM processor and is not really a general purpose computer. I mean, okay, the phones and the tablets and the switches, the TV to a certain extent, you can run applications on it and so forth. The Sky Q boxes, you've got Netflix on there now, the Fire TVs. But the things in the right-hand column are not really general purpose computers. They're kind of single-use devices or very limited-use devices, but we've still got software running on them, and they're still communicating over the Wi-Fi with each other to do things. And so it's becoming increasingly important to be able to develop software that runs on things that aren't what you would think of as a computer. And I'm trying to put useful stuff in here so that you can leave and kind of go, that was interesting to me, I'm going to go and investigate more into that and start building my skills on that. And so if you want to kind of be ready for this next wave of things, we could call it the Internet of Things. Has somebody coined that already? I'm claiming it. Then you can go, you can leave here and, or just right now, get your phone out, go onto Amazon and order yourself a Raspberry Pi 3B+. This is like 1,000 times more powerful than anything we had in 1989. This is the kind of standard for an ARM processor. You can run Linux on it, you can run Ubuntu, you can run Windows 10 Core on it. You can program it with .NET Core or C or Python. You can do all sorts of things with the Raspberry Pi, and you can use it as the basis for a kind of hardware project before you take it to the next stage of working out exactly what hardware you need. That's a reasonably powerful thing. If you want something a bit more powerful, if you want something that you can use as an actual games console to run retro games, then you can get the Asus Tinkerboard. This is a really nice piece of kit. These are about £60. And they're pin compatible with the Raspberry Pi, so you can use the same devices and hats and things. If you want to go smaller and have something that doesn't have very much processing power at all, but still runs Linux and has Wi-Fi and Bluetooth and 512 megabytes of RAM, then this is the Raspberry Pi Zero W. The W is for wireless, so there was one before that couldn't connect to anything, which is kind of why. But you can get one of these, and you can use this as the basis for your automated, artificially intelligent waste paper basket. So you can attach a microphone to it and say, waste paper basket, come here and open your lid, and it'll just try and drop things in there. So yeah, you can get those. There's lots of these boards at the moment. It's a big area. You can get a Hummingbird, an Orange Pi, a Banana Pi, an Odroid. Those are all computers. Those are single board computers that run an operating system. You've also got Arduino, and Arduino is a bit different. That's a microcontroller. So Arduino, it's not a general purpose computer, and it doesn't have like file system and all this sort of stuff. You load code onto it, and it just runs that code without having an underlying operating system. So that's why Arduino is in brackets, but still lots of fun to be had there. And to get started with this is NDC. I'm assuming most people are kind of .NET developers. You can get .NET Core now to compile to ARM64 and ARM32. There's the Core RT project, which does ahead-of-time native compilation. Don't ask me where that's at with returns to support and everything, but it's there. There's a great website, jsandler18.github.io, where he will teach you how to build your own operating system from the ground up for the Raspberry Pi. If you follow Alexandra Mutel on Twitter, he's XOOFX, he did that course in C# and .NET and compiled it with Core RT and created a Raspberry Pi operating system using C#. Microsoft, it's not early preview anymore, and it's not on MyGet. It's now part of .NET Core 3.0 Preview 2. System.device.gpio gives you drivers for talking to the GPIO pins on the Raspberry Pi. And that is a first-class feature in .NET Core 3.0. If you want something a bit higher level that gives you kind of nice drivers for things like cameras and microphones and so forth, then unosquare.github.io/raspberry.io gives you nice, friendly libraries for talking to other bits of those things. So that's probably not a bad thing to at least be starting to be aware of, because we are moving away from big systems and big computers, and we're moving more towards building computing into almost every aspect of our lives. So that's something that's a trend. We also have now the things that are effectively primitive technology today. So there are things that we've just kind of started iterating on in the same way that 30 years ago we thought that printer was pretty neat. A dot matrix printer, which hammered pins through a ribbon onto a piece of paper. You could get color dot matrix printers, which hammered pins through 4 different colored ribbons. And so each line that they printed, they'd have to go backwards and forwards 4 times through each of the different ribbons to build up a color image. And now we've got 3D, we've got photo printers and everything else. But actually, one of the things that we're very much in the early stages of is user interface. So user interface at the moment is either a touch screen or it's a screen with a keyboard, and you sit there and you type and you drag a mouse around and all this sort of stuff. We're just hitting possibly the next stage of user interface design, which is augmented reality or virtual reality, where you get into a digital space and you interact with it using natural gestures. This is coming out in Q1 this year, according to Oculus. This is the Oculus Quest. Who's got an Oculus Rift or an HTC Vive at home? Okay, so I mean, it's awesome. The Rift and the Vive are both, or Vive, I don't know how it's pronounced. I've only ever seen it written. I've played with a Rift, and it is immensely cool, but it's also it requires a £1,500 to £2,000 computer with a really good graphics card in order to make it work, and you're attached to that computer by a big thick cable, and you can't exactly wander around a lot. The Oculus Quest, there's already the Oculus Go, which is like a Gear VR that you don't need a phone for, but they're just about to start shipping the Quest. This is almost as, so it's got most of the same functionality as the Rift, 6 degrees of freedom, it's got the 2 touch controllers, it's got roughly the same resolution, but it is an entirely self-contained headset. So that's it. What you can see on the screen there, that's the whole thing. You don't need a computer. It's got a Snapdragon 835, which is actually 2017's phone CPU. And they reckon that it's got roughly the performance of an Xbox 360, which is just nuts. And this is going to ship for 400 quid, which is the same price as the Oculus Rift, and you don't need a PC. And you can put it on and just wander around with it, and it's got inside-out tracking and all sorts of stuff. And now that these are starting to actually, the controllers and the SDKs are getting more mature, we're starting to see some actual sensible software get built for these. I want to show you my favorite example from last year, which is Beat Saber. Has anyone played Beat Saber? So this will be boring for you, but if you don't even know what it is, check this out, because this is awesome. Nope, it's not awesome. Why won't my video play? Okay. Sorry? No, it's on the machine. Okay, so yeah, that's Beat Saber, which is like amazingly good fun. Almost got them sued by Disney/LucasArts, but it's a rock band style game, except you're hitting musical blocks with lightsabers, and you look like a total tit while you're playing it, because nobody else can see what you see, but you got that music banging away in your head. That's currently available on PlayStation VR and Oculus and Vive, but that's going to be one of the launch titles for the Oculus Quest. And it's not particularly complicated graphics or anything, so you're just going to be able to go, you know, I'm going to Beat Saber, yes. And that will pretty much be your cardio as well for the day. So that's pretty good. That's virtual reality. The other thing we've got is Microsoft HoloLens augmented reality. So virtual reality, you put a headset on and it transports you somewhere else entirely, and if somebody walks very quietly up, they can punch you in the face and you won't even see it coming. Augmented reality lays digitally generated assets over the real world. So you've got a see-through lens and then it lays stuff over it. The first thing we got that actually did this was Microsoft HoloLens. You may have seen Raphael did a talk about AR, the current state of AR. In about a month's time, so towards the end of this month, Microsoft are doing a press conference in Barcelona at the Mobile World Congress, and the guy who does HoloLens is going to be there. So while they haven't said HoloLens 2 specifically, fingers crossed, we're going to get to see it. HoloLens is a mystery Intel CPU that was made specially for Microsoft. It's got their holographic processing unit, 2 gigs of RAM. The main problem with HoloLens, if you've had a play with it, is it's got a 35-degree field of view, which means it's like holding an A4 piece of paper out at arm's length. That's what they can actually fill. And if anything outside of that just disappears. HoloLens 2, this is just rumors, but they're talking about a Snapdragon 850 CPU, which is the one that they're currently using for Windows always-on laptops with LTE and so forth. The second generation holographic processing unit, which has got built-in tensor cores for doing artificial intelligence, a 70-degree field of view. So that's like, what, holding up an A3 piece of paper? That's probably going to be fairly decent, actually. And let's hope that's what they're going to be telling us about at the end of this month. There's also Magic Leap, which finally went from, yay, look, we're going to make this amazing thing that makes whales leap out of the floors of gyms and crash down, and actually landed, and it was this. And yeah, they'll get there eventually. But you can get one of these now. You can order, well, you can get one of your friends in the States to order one for you and then ship it over to you. But this is fairly decent. Let's see if this video will work, shall we? God damn it. Crap. I don't know why these aren't working. I hate my life. I've got some grabs from it. This was the launch thing for the Cheddar Live News. How can I not be doing any coding and still have my demos not work? That's just not fair. One of you is a Jonah and you're following me around. This is an app called Cheddar Live News, and it's basically this guy's just wandering around his house, and he's got the little Magic Leap controller thing in his hand, and he puts his Magic Leap on, and he just starts walking around the house, and every now and then he goes click, and a screen just appears in front of him with the news on it, and you sort of think, oh, that's really impressive. Now you've got a TV that follows you around, and you don't have to stay in one place to watch it. There are a couple of problems with Magic Leap, and obviously the first one is, oh my God, cool shades, yes. Maybe in your house, if either you're the only one there or everybody else is also wearing Magic Leaps, then you can just about get away with that, but you're not going out looking like that. But the thing with this is, and with HoloLens as well, is this is primitive technology. This is us building effectively the prototypes. So what Magic Leap have built here in technology terms is the Newton message pad. And over the last 25 years, the Newton, well, it took 13 years for the Newton message pad to go to the first iPhone. Which got a lot smaller and a lot lighter, and the battery lasted longer, and we went from 640 grams to 135 grams. We went from 2 colors to all the colors. We went from 640K of RAM up to a gigabyte of RAM. So these things get smaller and lighter and more polished and more usable fairly fast. And so it doesn't seem that unreasonable to suggest that what is currently a fairly big, chunky, stupid-looking thing that you're going to stick on your head and hide from everybody will, by 2031, let's say, have become something that looks like a fairly small pair of sunglasses. Not necessarily those sunglasses. Those are just the ones that were easiest to remove the background from when I stole the image from Google Images. But this Magic Leap right now will already put these screens in space in front of you. It looks something like this. So he's actually got multiple screens here. There's this screen here, which has got Cheddar News, and there's this screen over here, which is charting something, maybe it's his microbrewery that he's got running somewhere, and that's how the beer's fermenting or something, because he looks like that sort of person. But this does raise the possibility that this might be, the 2020s might be the last decade where we have these things, or screens on our laptops. or projectors and big screens up at the front here. Because if we can make screens just pop into existence in front of us, wherever we are, and whatever size we need them to be, then that's going to be so much better. My computer can be reduced down to a keyboard. I'm guessing the screen that appears in space in front of me is probably going to be touch. Be weird to have to use a mouse with a screen that's not really there. And the thing is, we'll get that because we do technology jumps in really weird stages. So we kind of go, we can make anything appear in front of us and we can do anything with it. Let's make screens appear in front of us and carry on presenting two-dimensional flat rectangles of information for us to interpret. But that's where we'll go first. But we'll eventually, who remembers this from the HoloLens launch demo? This guy walks into a room and goes, I'm playing Minecraft. And it maps the room, works out where all the flat surfaces are, and goes, Minecraft. And he even put a bit of TNT in the wall and then blew it up. And it blew a hole through the actual wall, and you could see Minecraft outside. And so that's going to be the next stage, is where we're kind of just creating whatever we want to create and sticking it in the world around us and interacting with it as though it's really there. There's one thing that I didn't have a chance to put into this presentation because I was too busy doing my PubConf talk, which I only found out about yesterday from Raphael, which is leap motion. So the guys who did the little aluminium Mars bar that can see all your fingers, they've got a kind of 3D print it yourself and build it yourself thing called Project North Star, which actually looks completely nuts. Because one thing Leap Motion are really good at is tracking what your hands are doing. And so this is their view of what augmented reality is going to be like. And it's just like, so hold your hand out like that. It's got tabs down the side of it in your vision, and you can pull one of them out, and that's your mobile phone. And so this is, whether this is 10 years, 20 years, 30 years, this is where things are going. And once it gets down to the point where it's basically a pair of sunglasses, then it's not going to be a matter of whether you're going to wear these things or not. It's going to be a matter of whether you buy them from Ray-Ban or Oakley, who are going to become the supercomputer manufacturers of the fourth decade. This is a really nice, this is desktop augmented reality, which you can build with ARKit, which is Apple's thing, and I think it works with AR Core as well. But yeah, you can start building augmented reality experiences today, or virtual reality experiences today, to be ready for when it comes time that your business says, we're throwing out all the screens and replacing them with contextual information mapped onto reality. So if you want to be ahead of that curve, the things that you really need to know is you need 3D graphics and modeling. So you need to understand, I always like to compare this to when I was learning programming on a ZX81 back in 1982. If you wanted to print something at particular coordinates on the screen, you would say print at 10,12, and it would go 10 in and 12 down, and then print whatever you wanted it to do. We now have effectively render at, and we just have an extra coordinate. But then you also have to worry about the rotation in three-dimensional space and the size, and you've got all these transforms and everything you have to do. It's quite complicated, but the SDKs that are out there make this quite easy. And you also need to start getting into spatial design to make sure that you leave enough space between things and that they're relating to each other properly, and that if this thing's supposed to be in... You see the new Pokemon Go with the new ARKit stuff, if the Pokemon is this side of the lectern, I can see it, but if it goes round the back, it can actually peek out from behind a real thing, and it clips off the bit that's behind the lectern, even though all it's actually doing is drawing something right here, but it works out. So, this is the stuff that we need to be getting into. And the new interaction models, so following hands around in space and working out what they're doing. And again, this is something that for .NET developers, probably the easiest way to get started with this is with Unity 3D, which is a games engine Or it started out as a games engine, but if you look at what people are doing with it now, they're doing business applications, they're doing automotive applications, people are doing all sorts of things with Unity now. And it doesn't matter if you're an artist or a 3D person or whatever, they've got an asset store, and you can go to the asset store and say, I want penguins. And it goes, here's everything from a high definition, absolutely realistic emperor penguin to something that looks like a penguin made out of Lego. There's an engine kit called, a guy who makes engine kits, and he has a website, moremountains.com, and he does a driving game kit and stuff. It's a really good way to get started. If you're looking for a book on that, I recommend Unity in Action, 2nd edition from Manning Press. You can go onto YouTube. There's a guy on YouTube who just seems to support himself using Patreon. Search for Brackies, and he's got loads of tutorials on there. And there's some great code tutorials on how to actually program three-dimensional objects and graphics and so forth using things like sine and cosine and tangent and various other bits and pieces. That's on catlikecoding.com. There will be a link to links at the end of the talk, so don't worry too much about that. So that's where we're going with UI and user experience, in my estimation. The next one is manufacturing. And manufacturing, at the moment, pull raw materials out of the ground, take them to a factory, the other side of the world, make them into the thing that you want them to be, then take them back to the other side of the world, put them into an Amazon warehouse, and let people order them, and then take them to wherever you ordered it from in sometimes as little as 2 hours, which is just nuts. And we think that's pretty good. But where that's going to go, I think, is 3D printing. So 3D printing, this is the 3D Systems stereolithographic apparatus. This was the first 3D printer in 1992. Stereolithographic is where you cure resin with a laser beam and gradually extrude an object from a liquid resin. This, in 1992, would set you back $100,000. Okay? This is the version 1 RepRap, reproducing rapid prototyper, or replicating rapid prototyper. This was invented at the University of Bath. Well, it's invented all over the place, but they built this one at the University of Bath in 2007, so 15 years later. And you could order some bits, you could get some bits of wood, and you could get some bits of tube, and if you knew somebody who had one of these printers, you could print all the other bits yourself, except the circuit boards. And so that was why it was replicating, because you could use a RepRap to make a RepRap. That was 2007. 12 years later, you can now go onto Amazon and search for 3D printer, and you'll just get pages and pages and pages of things that cost less than £200. And you can get yourself a 3D printer and hook it up. And I absolutely recommend it. It's great fun. You can just make almost anything you want in almost any color, as long as it's all the same color. So a lot of these are actually just kind of multi-generation later RepRaps. But we're starting to see things. What does that look like to you? Because to me, that looks like an iMac. Okay, so we're already at the point where somebody has taken the concept of a 3D printer and turned it into a consumer product that looks like it's been designed to sit on a table in your living room. And this costs just over £200, and it's by all accounts, it's a very good 3D printer. Okay, that will print, so you can print one color at a time. If you want something that's multiple colors, you have to break it down into the bits that are different colors, print them individually, and then glue them together. Unless you've got just under £1,700, in which case you can get this. Same company, this is a color 3D printer. I didn't know when I started doing this research for this talk that this existed, but this comes with a essentially blank resin, blank filament, and it has an ink tank with colored ink in it, and as it's printing, it mixes the colors with the blank filament, and it will do full color 3D printing. And it's £1,700. That's less than I spend on my laptops or on my desktop machines. I spend more than that on lots of things. I'm definitely getting one of those as soon as I've managed to hide £1,700 under the floorboards where my wife doesn't know about it. Now, admittedly, at the moment, that's still at the dot matrix point of things, okay? So it's still low-resolution printing. But you can do high-resolution printing. This is the Form 2 from Formlabs. This will cost you, this is essentially the same technology as that first SLA. So this is, you get resin, and it uses a laser, and it cures it. And this does really high-resolution 3D printing. This will set you back around £3,500. So you can have this, or you can have 2 full-color 3D printers. If you spend £5,500, you can get a wash and cure set that go with it, and you've got like a proper in-your-house manufacturing process. The only issue with this, so if you go for one that works with the tube of filament, those things cost about a tenner for a roll of that filament. If you go for this, then a bottle of the resin that this uses to do printing will set you back £150. So this is not a cheap thing. But if you want to actually go into business manufacturing and designing things and you want to prototype stuff, then this is great. And you can, that's not an unreachable amount of money. This is the sort of thing it prints, and you can see that it's really nice, high resolution, very smooth things, and you get different colored resins to do different colored things. And this is just at the start of the printing, 3D printing technology. So again, from 20 years, in 1989, we had a 2-color dot matrix printer with that lovely noise that it made. 20 years later, we had the HP Photo Smart A626, which you could take your memory card out of your camera and plug it into that printer, and it would produce prints that were every bit as good as the ones that 5 years earlier you'd have had to take a film into Boots and have them develop it. By the way, that is why some of the earlier stuff in here, the photos of those things are not that great, because we didn't just carry cameras around with us all the time. If you wanted a photo of something, you had to have a camera and put film in it and then take the photo and then go and get it developed. And then somebody between now and then would have had to digitize it and put it on the internet. So yes. In the very near future, and we're kind of, this is already stuff that exists in laboratories, there will be 3D printers that can actually print gadgets, just no additional bits need to be put in. They've got lots of tanks or supplies of various different materials, and somebody has actually successfully used a 3D printer to build a functioning remote control for a television. They didn't do anything to it. There was no assembly, there were no components put into it. It built from essentially raw materials a functioning remote control for a television. That exists now. So again, extrapolate that forward for a bit. Also, food. So we actually have quite an issue with food. We're kind of running out of it. Farming it is very intensive. There are going to be 10 billion people in the world by 2049, and we need to feed them all. And so that's quite tricky, even farming that much food. But that is another thing. This is 3D printed meat. It looks kind of gelatinous there, and you kind of go, I don't really want that. That looks like orange jelly. I like orange jelly, but I don't want it in a burger. But apparently when you cook it, then it goes and it looks like cooked meat, and it feels like cooked meat, and it tastes like cooked meat. In the far future, and by far future here I am talking about maybe 30, maybe 50 years in the future, we are just going to get to this point where you go, computer, make me tea. The way the replicator worked in Star Trek was it condensed energy into matter, which was, we may be a little way from being able to do that. There's a book, if you haven't read The Diamond Age by Neil Stephenson, I highly recommend it. This is about a nanotech future where essentially there is a feed. So in the same way that you have water and electricity coming into your house, people just have streams of molecules coming into their houses, and printers that can assemble things out of atoms and molecules. It's called diamond age because if you're making things from atoms, carbon is more abundant than silicon, and so diamond becomes cheaper, effectively, than glass. And so all the windows and everything in this world are made of diamond instead of glass, which is nuts. It's a great book. Highly recommend it. And then, of course, we need to talk about artificial intelligence, and I've got 5 minutes left to cover the whole of artificial intelligence, so let's do this. So, artificial intelligence started about 70 years ago with Turing, when I know if you can't tell a difference between a computer and a real person, then that computer is intelligent. In 1956, McCarthy and Minsky coined the term artificial intelligence at a conference. In 1973, the Lighthill report came out. For all the research that was being done into artificial intelligence, the Lighthill report said machines would only ever be capable of experienced amateur levels of chess. And for us futurologists, because we're all futurologists now, right, this is something that we'll have to come up against repeatedly, where we say this is going to happen, and people go, oh no, that's a bit far-fetched. And it doesn't take long to get to the point where we prove them wrong. 1980s, bit of a bust. Expert Systems, Prologue. Just ignore the 80s, they don't really count. 1997, though, Deep Blue beat Garry Kasparov 3 games out of 4 at chess. Ha, Lighthill, shut up. In 2002, the first consumer artificial intelligence popped up with the Roomba, which is just the little robot that will go around and hoover your house. As long as you don't have kids like mine who make it impossible for Roomba to go more than 3 feet without bumping into one of their sodding toys. In 2005, this is when Boston Dynamics made that dog that could run across battlefields. In 2005, if it fell over, that was it. That was your 10 million robot. But now, it can get back up again. And if it can't get back up, it calls another dog that's got a special thing attached to its back. Have you seen the one where one gets to a door that it can't open, so it calls its door-opening friend? Have we learned nothing from Jurassic Park? So yes, in 2011, IBM's Watson played Jeopardy, and it played it properly. It played it by listening to the questions that were being read from the thing. It asked for them off the board, and it worked out the answer, and then it put it in the form of a question, and it trashed the 2 human Jeopardy record-holding champion people. And that was like a massive supercomputer, and it cost millions and millions of pounds. But also in 2011, Apple released Siri. And in 2014, Amazon introduced Alexa. And also in 2014, we got the first driverless cars actually driving around California. And so far, they've only killed 1 pedestrian, which is quite impressive. They got millions of miles on them. I've killed more pedestrians than that. And I've probably only driven about 200,000 miles in my whole life. And they deserved it. In 2016, Google invented the Google Assistant, which fucking spies on you. Also in 2000, so when Garry Kasparov got beaten by Deep Blue, they went, oh, well, chess, though. Chess is quite easy. Nobody will ever beat a human player at Go. So, yes, spin forward another 19 years, and AlphaGo beats a 9-dan professional 4-1 using a Monte Carlo. They didn't even teach AlphaGo to play Go. They just went, here are the rules of Go, and it played against itself for a bit. It actually worked it out from base principles. Now, we have neural processing units. So the A12X, most of those 10 billion transistors, most of those 5 teraflops that it can do are in its neural processing unit that exists just to do AI. And it's mainly to map the world around it and everything else. We've got NVIDIA putting tensor cores into their CPUs and their GPUs. The Snapdragon 855 has got AI circuitry built into it. The HoloLens 2 has probably got something like that. We can program chips out in the field. Field programmable gate arrays are being used for artificial intelligence. It's really difficult to write this stuff, so you can just go to the cloud and go, hello, I would like to consume some artificial intelligence and machine learning, please. Microsoft Cognitive Services, Google Cloud AI, IBM Watson as a service. You can do all these sorts of things. If you want to start mucking about with this, and trust me, you do want to start mucking about with this, if this is the one thing that you take away, make sure that you are at least keeping pace with the development of machine learning, because this is the thing that's going to change all of our jobs within the next 10 years. If you want to go home and get something to play with, Microsoft's machinelearning.net. If you're a .NET guy, you like C#, then ML.net. There's lots of great examples. You can go and start working with that. OpenCV, the Open Computer Vision project, that works with Python, C++, Java. I think there are mappings for C# for that. Keras is a deep learning library for Python. Google's TensorFlow is incredibly powerful, but oh my God, it's difficult to use. If you want to build your own assistant, then there's Mycroft as well. So you can go and you can get all of these things from these various websites. Again, there are links coming towards the end. So we've also got quantum computing, which I really don't have time to go into, but there are some links on the thing that you can do that. If you want to get started with quantum computing, then there's a quantum development kit that you can play with, and there's a great book called Computing with Quantum Cats by John Gribbin. Nanotech, which is the diamond age sort of stuff. We've got nanomaterials and multiple ways of building nanotechnology, biomimetics and speculative things. If you want to get started in nanotech to get ahead of the curve, then get a bachelor's degree in material science, get a master's degree in material science, get a PhD in material science, and apply for a research position at a really good university. So like Oxbridge, Harvard, MIT, not Princeton. All right, maybe Princeton. So I am a bit over. I'm going to take a couple of extra minutes because I just want to say this is where I think we're going. So next 10 years to 2029, none of this matters because we're getting hit by the Apophis asteroid. There's a 1 in 150,000 chance, but I'm really counting on it because I'm going to be at the top of a mountain going, bring it! Because I'm tired. But no, I think in 10 years' time, augmented reality is going to be pretty much everywhere. Whether we'll be using it walking down the street, chasing Mario coins on our daily run, I don't know, but we will be using it a lot more, and it's going to start changing the actual shape of the world around us, because a lot of things won't need to exist anymore. It just needs to look like they do. We will have self-driving vehicles, self-driving lorries that stay in the slow lane on a 2-lane dual carriageway and don't try and overtake because they can go, anyway, it's a bit of a thing there. We're going to have automation in things like manufacturing and farming and logistics and knowledge work, and we're going to start seeing massive job losses, and society is going to start to fall apart. In 2039, I really hope Elon's going to have some things landed on Mars by that point. When they go to Mars, they're going to be able to do that in part because they're going to be able to take 3D printers with them that will be able to just pull materials out of the surface of Mars and build whatever they need when they get there. We will no longer be getting things delivered by Amazon. We will just be buying the blueprints for something and printing them in our houses, because we're going to start to hit the start of the nanotech age at that point. Robots will be doing pretty much all the jobs by that point, and we will be learning to improve ourselves and augment ourselves and offload tasks to artificial intelligence to help us do things and all this sort of stuff. And by 2049, we will either be living in a utopia with robot dogs that we are taking for a walk at the end of our extended arm. But there is no reason, if all these other things, 3D printing and artificial intelligence and everything else, there's no reason by 2049 why we could not be in the post-scarcity society of Star Trek, where we don't actually need capitalism anymore because there is enough of everything for everybody. The other alternative is that everything's melted and we're all at the bottom of the sea and none of this fucking matters, in which case I just, whatever. But yeah. That is where I would like us to get to, and I'm optimistic. So if there is anything in this talk that you were interested in and you want to learn more about it, I made a website. I've never done this before. I made an actual website that you can go to right now. This isn't an I'll do a git push. You can go to the website. There's links to all the things that I've talked about in this talk, ML.net and artificial intelligence and all this sort of stuff. Sorry for going a couple of minutes over. I hope you think it was worth it. I hope you had a great conference. Hope to see some of you at PubConf and other people at other conferences. And thank you very much for listening to me. Goodbye.